Yeah. Okay.
I think I got a stress ball over there.
Yeah, I know, it's been a long semester. Well, anyway, this is the last lecture, and I did get a haircut. It's not looking exactly the way it was looking back in the classroom. So, we are going to finish the book today. We're going to just do the last half of chapter 14. I'll launch the exam 6. In fact, it's all ready to go at the end of this lecture. I think exam 6 is relatively, it's easier. It's a little lighter than most of the other exams.
Lots of true false?
Well, not a whole lot of true false, but just, a lot of it's just kind of common sense. And, looking through chapter 13 and 14, and as long as you're kind of hitting the high spots, the subsection headings, you won't have a problem on that at all. There might be a couple tricky ones. I mentioned, I think it had something to do with the amount of oil spilled in the ocean versus other pollutants, but so just when you're, it was a similar problem that tripped up a lot of people when they were looking at the relative amount of energy left. So you're looking at like reserves to production ratios. Be sure you're looking at the ratios and not just the numbers. So, okay, so chapter 14, and I think we're ready for 14.6, which is called Harnessing Renewable Energy Sources. And so these authors believe that moving away from ancient carbon energy stores and towards renewable energy stores is one potential remedy for some of the environmental issues we're facing. And I also want to reiterate that there's no one magic bullet. I mean, every technology has its downside, and as I said before, a lot of times it just comes down to picking one's poison. Another thing it's worth mentioning right now is that there's just a little bit of semantics that I sometimes have trouble with. So if you're listening to the popular press, you'll hear someone say, "Oh, that's better for the environment." Well, I tend to take the sort of the opposite approach and say there's really nothing that you can do good for the environment. There's only things that you can do that are less bad. So, and again, it's just a little bit of semantics, but you might say, well, something that's less bad is in fact better, but maybe the better way to say it is, well, just less bad, not as bad, or this one's worse than the other. Because even this little technology we're looking at right here, we're on page 603, principle of a central receiver power tower. What we're looking at is a way to take solar energy and actually turn it into electricity. And I guess maybe there's one more figure we want to see that's a little bit simpler. This is a solar thermosiphon where you're just taking solar energy and turning it into heat. So you're trapping this, maybe 1 square meter. So this is maybe a 1,000 watt unit, and storing hot water. This can then go off for cooking, showering, cleaning, etc. But if you get the water even hotter, the same principles that are in place in a coal-fired power plant where you're making steam to turn a generator are at work. So instead of setting something on fire, just use this array of mirrors, shine all of that at a central receiver. Water gets hot, goes through a cycle, and then again makes electricity. So making electricity directly from the sun without setting anything on fire. We're still dealing with a Carnot efficiency on this guy. So if you remember your Carnot, Carnot efficiency, eta equals T hot minus T cold or T low divided by T hot. So if we look really carefully at this figure, maybe I'll zoom in a little bit. we'll be able to see that this central tower is almost just glowing white hot. So see how, so that guy's just white hot. The point is to get it, to be more efficient, you want that to be as hot as possible. The low temperature is just whatever the surrounding air temperature happens to be. Because this, there's still a steam cycle going on in there. And there are actually other cycles as well, but the Carnot cycle is just sort of the easiest to look at in terms of temperature differences. Okay, so that's concentrated solar power. If we looked at the solutions project, the one that I talked about in my Billings talk, concentrated solar power is a big player for Montana's 100% renewable energy future. Just imagine several square miles of that replacing Colstrip. Colstrip runs at 2 gigawatts. And also, while I'm thinking about it, another way to think about the energy footprint of our landscape, I just want to give you a little thought experiment, and this might help you think towards the final two. So and this might also help you think of, if you ever take calculus, it might get you thinking in that direction as well. So let me just draw the ground, something like this. So just, I've got the very top surface here is the top surface of the Earth. And these other sheets that I'm drawing are just kind of looking backwards in time. So let's just say this is, time equals 0, so time 1. And just imagine taking this solar array that we see right here and plopping it down right here. So there it is on Earth. The sun is up here, shining down. The CSP, concentrated solar power, makes electricity off to the grid, right? That's what you want. The business as usual approach, the conventional fossil fuel approach, is going after all of this stuff. And, we did the problem the very first day of class. We got the 10 million to 1 ratio. So really what's, you can almost think of the fossil fuel industry as time travelers. They are traveling back in time, and rather than using a technology now to do this. So this is a new electron. So I'm just N for new. A new electron that was a photon, that I'll put as a phi, a relatively new photon sitting there in the sun. It's also worth mentioning, this is kind of weird to think about, but photons that left the surface of the sun 8 minutes ago spent something like 9 million years inside the sun. That's kind of how long it takes them to kick around. Didn't know that until pretty recently. So that photon itself has done some time traveling. It's pretty old. By the time it gets here, there's, sun's a big place, kicking around, takes a long time to get through traffic. If you thought reserve was bad, try the center of our star. But anyway, the point I'm trying to make is, what we're looking at with technologies like this are relatively new photons turning into relatively new electrons. Down here, you've got your coal, but of course, that coal got here a really long time ago, and the surface of the Earth used to be up here, now it's buried. But just think of these as very old photons. We dig them up, send them to the coal-fired power plant, and then here they go, electron, and I'm just going to call that an old electron, because that energy was stored there a long time ago. So that's kind of the big picture in how to think of these things. And so your electricity is still solar powered. It's just that the solar, that photon hit the Earth a long, long time ago. Okay. Now, Here's another example. We're just looking at some PV panels being installed on the roof of one of the Open University's buildings. So that's the publisher that publishes this book, and if you get into 102, we talk about the physics of PV in a lot of detail. If you take NRGY 243, you get into the installation practices of that. We're also very fortunate right now with our National Science Foundation grant that we've got $140,000, some of which is from the NSF and some of which is from Northwestern Energy to build a mobile PV installation trainer. So little smaller than this building, but just imagine this on wheels, and then we can take this out in the community and do PV, hands-on PV training with it. We do some here. We built PV systems in the practicum. We built one last year. We built one the year before that. But and frequently we do have opportunities. In fact, this spring we'll have an opportunity to help out with the Lomason installation. So we got a Quelf grant last year. Mark Hansen, who graduated in 2013 or 2012, put a lot of work into it. It was funded, and Solar Plexus has been contracted to put that on, so that'll be part of our hands-on for 243 in the spring. And yeah, so plenty more opportunity to learn about photovoltaic installation. Okay, now the authors then go on to mention what's called indirect use of solar energy. And if you remember, back early we talked about, what energies are solar versus not. Well, bioenergy is a form of solar energy. If you take, or sequestered solar energy, if you take Brian Kern's courses, he teaches alternative fuels 241 and biomass 244. You'll get really deep into biomass or bioenergy. There's what's called traditional biomass, and that's just kind of what nature provides. Go cut down a wood, set fire to it. There's modern biomass, and this can be the result of agricultural products. So straw is mentioned, some of which is coal-fired. Municipal solid waste is also mentioned. Brian Kearns gets into that, and we've got some neat partners here in town who have some waste-to-energy technologies that we're currently developing. Biogas is also mentioned in the textbook, so allowing anaerobic digestion, and I think we all know what that smells like. If you're ever have a chance to get on your rooftop and you go and see the one little tiny hole, you'll know exactly what I mean by biogas. But there's a lot of methane in there, right? And it's still flammable. There's still energy. Biofuels are also mentioned. That's page 606. So waste vegetable oils. And it's also stated here right at the bottom of biofuels. It says biofuel use is potentially controversial. It can be seen as being in competition with the use of crops for food. I had the same question a few years ago when, there's a hunger problem on this planet, and then to see the U.S. subsidizing corn growing to then be used as a fuel, I had problems with it too. When tortilla prices go up and people are going hungry across the planet. So I don't know where you go with that. It's tough, and I guess I also in terms of looking towards a future with 100% biofuels, I have an issue with burning ancient petroleum products to harvest. It's the same problem that I just drew here. You might have instead of your concentrated solar, you've got your you might have your purpose-grown, biofuel. There's biojet fuel, there's biodiesel, et cetera. That's all, again, relatively new photons hitting the planet. But how are we harvesting that? Well, frequently with a, conventional tractor that is getting its, fuel from again, these very old photons. And eventually, once all those old photons are gone, we have no choice but to move to 100% renewables, but that's kind of the cycle that I see there. And I guess the bottom line is we're just in a point of transition right now. Okay, hydroelectricity is also mentioned. That's also an indirect sun. The sun evaporates water, that goes up, goes behind a dam, you make electricity. Wind energy is also indirect solar. Thermal gradients cause winds to blow, put it through a turbine, make electricity. And these are becoming more and more common. Here's a shot of a wind farm in Scotland. That's an example of onshore. Here's an example of offshore, and these are becoming more and more frequent. So that's also, again, the sun drives thermal gradients, which drives wind. Same thing here. Waves are driven by wind. The wind is driven by the sun, and what these researchers are doing is basically putting a big articulating sausage, if you will, out in the middle of the ocean, and then allowing the deformations that occur between the different segments to make electricity. So just, in a wind turbine, you've got a generator that spins around. We talked a little bit about Maxwell's relations, the relationship between electricity and magnetism. In this particular scenario, you don't have something continuously spinning, but as long as you have something moving back and forth, it's essentially rotating. You put it through a rectifier circuit, and then you can make electricity from that. Okay, so again, that's indirect solar. Okay. Non-solar renewable energies, and there's a chapter for each one of these things that we're just kind of blowing through right now in your 102 text. And if you haven't registered for 102, please do. There's just we need.
As soon as I'm done taking my alcohol training.
Take your alcohol training, by goodness, and get on in there. Yeah. So tidal energy. Now you might argue, well, there's a solar tide, and you would be right in that, but it's not a photon related deal. It's a gravitational type of energy. So tidal barrages, tidal systems. I talked a little bit about energy densities of tidal systems in that first paper, that 2008 paper that you read. Tidal barrages. And I think last time we might have even talked a little bit about China and their island building lately. If you start building islands and you connect them in such a way, I mean, you have to have a bridge to get there. And since there are tides in the ocean, one could imagine under this bridge building an articulating wall. So when the tide comes in, it goes behind the wall. And then as you're letting the tide out, you've got generators just like you would see in a hydroelectric dam. So this could be an example of a barrage. And these are just free stream generators. So if you've ever been, in like the San Juan Islands or somewhere like that, there are some pretty substantial tides, almost to the point where you feel like you're swimming or rowing in a river. And so setting a technology up like this in a relatively high flow zone is a way to gain access to that energy. And again,
No swimming allowed, of course.
Beg your pardon?
No swimming allowed, of course.
There's swimming allowed. There's no lifeguard on duty. Die at your own risk.
Yeah.
Who's the guy?
Off this tower, so don't rush.
Who's the guy? Wasn't he? I think the CEO or the owner of North Face just died. The clothing company or whatever. So 70-year-old man, 72-year-old guys out there kayaking in a river somewhere, flipped over and drowned. But die at your own risk, doing what he loves.
I guess he should have had that Columbia kayak flipper device.
Yeah.
Since it's Columbia, he refused to buy it.
Yeah.
Or something, I don't know.
Maybe not branded properly. Yeah, I don't know. I mean, it's of course very sad when someone dies, but on the other hand, probably died doing what he loved instead of in a hospital.
72 out kayaking.
Hospital bed somewhere, yeah, good for him. Okay, geothermal energy, this, and if you take 102, we'll get into this in a lot of depth. The energy here we can think of as just being left over from friction. You know, friction caused by initial collisions when the planet formed. So the average temperature of planet Earth used to be one heck of a lot hotter. Everything radiates. The Earth is radiating at a rate of 60 milliwatts per square meter. So if you go back, and that's another number to kind of keep in your back pocket, kind of fun to think about. It's like, oh, the Earth doesn't radiate. Well, the sun radiates and the moon reflects. But so the sun is radiating at 1,000 watts per square meter. The Earth, kind of wild, you don't usually think about it, but 60 milliwatts per meter squared. So that is energy that is leaving the planet because the planet is hotter than outer space. Where does it go? Well, it goes away. It goes into outer space. 60 milliwatts per square meter. That's the average. You look at an installation like this. There was somebody on the radio not too long ago talking about. Well, in fact, we did the math in 102, and there was a study that came out of MIT a few years ago that included all of the geothermal energy resource available on the continental U.S. They excluded Yellowstone because it's kind of an anomaly. Big hot magma chamber sitting there, a few hundred miles south of us. But we did the math, and if you extracted all the geothermal energy on the continental U.S., however many million square miles or million acres it is, 7 kilometers down, it's not that far. I mean, it's basically from here to my house. I mean, just right up the rattlesnake, 7 kilometers, 3 miles. So 3 miles down, there are 130,000 years worth of energy, thermal energy, beneath the surface of this nation. 130,000. So there's no shortage of geothermal energy, is sort of the point. One would not want to take it to the point where one cools the Earth's core to the point that it solidifies, because the spinning of the Earth's core creates our magnetosphere and deflects rays that would otherwise cook us. So don't get your hopes up too much and suck all the heat out of planet Earth. Not that we're anywhere close, but just the point is there's a lot more there than you might think. A heck of a lot more. And if we were smarter with our buildings, we would have them coupled with the Earth to a much greater extent. In fact, I heard recently, and this is a little bit of hearsay, and I don't know if it's true, but apparently you can't build a new house in Germany unless you put some geothermal in. The national building code in Germany requires a geothermal system for new buildings. Yeah. Okay.
It's pretty interesting down in New Zealand looking at all the different plants they've got.
Oh yeah, New Zealand's got big geothermal. Yeah.
Geothermal and wind,
Yep.
solar.
Yep. Yeah. Okay, so here we are. This is UK CO2 emissions. So we're now into section 14.7, and this is called Towards a Sustainable World Energy Future. Is that from, that must be from, did Dickens write A Christmas Story? Did he write, yeah. Oh, are these the shadows of the things that will be, or the shadows of things that may be only? Yeah, so we're trying to look into the future now, and we can see that the UK has, in fact, dropped its CO2 emissions. And I know we looked at Shramsky a little bit briefly. I'm going to guess, I'm not a demographer, but I'm going to guess that a lot of this is because the UK, I don't think they've lost population. They're probably relatively stable. You know, a lot of mature European countries are have their population stabilized or even diminishing. I think Italy's losing people, but what I see this as mainly an increase in efficiency. You know, more people get the insulation. You can see that gas has come online. As natural gas comes online, the number of kilowatt hours that you can get with a given amount of CO2 emitted goes down. So just by gas itself, what they're not really showing here, I'm sure it's in another chart that's not coming to me immediately, is the energy consumption, and I also assume that the UK is relatively flat on that as well. But you can also see that the UK is committed to curbing their emissions and really dropping them. And I think the numbers that I was hearing to avoid the 2 degrees Celsius increases is that we're really going to, by 2050, we're going to have to be at 10 to 20% of our emissions. Is that the number? Does that sound about right? We'll have to, by 2050, we're going to have to be at something like only 20% of our current peak emissions.
I know by 2030 it was like 25% or something.
25% reduction or 75% reduction?
75% reduction.
Oh, really? Okay, so it's even sooner. 2030, 75% reduction.
So they said by 2030, if we don't reduce it gradually, I don't remember the percentage each year.
Mm-hmm.
Montana will end up looking like
The moon?
the Nevada desert.
Yeah. Yeah. Well, I mean, here's an example. So we're looking at the UK at 700 million tons per year, and let's just do some quick math on that. So 75% reduction. So if we take 700 times 0.25 equals, we're looking at 175 by 2030. They're pretty close. They're aiming for aiming for 200. So yeah, I'm fairly encouraged by what's coming out of Paris right now, to be honest. I've seen a lot of protests, people saying that there's some companies out there saying that fracking is a solution, or some junk like that. I get a lot of these protest videos, but I don't know. I have confidence. I want to do it at my own residence. I'd love to just shut off my natural gas tap entirely. Go to biomass, sequester the carbon with these technologies I've been working on with some really talented folks. Get a big old.
Except for cooking.
For cooking, I would like to use hydrogen. I'd like to be able to. Burns like crazy, man. Oh yeah, yeah. Yeah. And one of our alums, Mark Broston, or use a biogas. Just use an anaerobic digester to make your own methane. But either way, if you're using combustion, if you're combusting a carbon product, you're going to make CO2, and you have to figure out a way to sequester it. If you burn hydrogen for cooking or cleaning, then your only emission is water. So exciting times. Time to go for it. Okay. I think we're still in the UK here. So A is, actually no, let's maybe take a quick break here. I think we're 30 minutes or more. Yeah, we'll take a break.